Okay, in the last lecture we had stopped at the point where we discussed the stopping criteria for the nonlinear iterations. Okay, and we had proposed one stopping criteria which was based on computing the residual at the residual vector r at the end of the current step, okay, which means this will be equal to, I would say, k I ai minus fi, minus of this. This is what we had said our residual is going to be. Okay, so here by putting the computed solution at the end of the step back in the calculation of the stiffness matrix, multiplying with the taking the action of it on the computed displacement vector minus fi, this is what we will call as our residual to be used in the computation of the error. Okay, so this computation, and we had said that essentially if the length of the residual vector divided by the length of the solution vector is less than or equal to some tolerance, then I stop. Okay, there are various stopping criteria which are in use, and the basic problem with all the stopping criteria is that we should avoid the termination of the solution process in a very preliminary stage. That is, if the stopping criteria tells me that the tolerance has been reached and my solution has not converged, then we will have a problem. So there are various versions of stopping criteria which are available. Another one which is available is by taking the length of the difference between the two solutions of the current step and the previous step divided by the length of the solution, and if this is the ratio is less than epsilon, then we stop. Okay, so several other stopping criteria are available. One can use any one of them. Okay, so let us now, what we had said, if you remember, reinitiate the discussion here, that here is my f, here is my delta, okay, here is my nonlinear solution corresponding to a particular level of the force of the load. Here is my first solution using the direct iteration, where we essentially solve for the linear part. So this becomes my delta 0. Okay. Then I come down as we had said. Okay, and from here again we said that we will recompute and so on. This is for the direct iteration. What we had said is, what if I come down here at the end of the first iteration, and instead of doing this, I do this. Okay, then I go to this part. So I have the earlier solution. To that, essentially I am finding a correction. Okay, so I had delta 0. To this I will add a del delta 0 to get delta 1. So I want to add a correction so that I get the new solution. And this computation of this correction to the previous solution is what we are interested in. Okay, so this will be del delta 0, this will be delta 1. And you see what it is doing, it is giving us faster convergence to the desired solution, this delta desired. So this is the basic idea, and what we had said, this method is the Newton-Raphson method. So today we are going to discuss this method in greater detail. Okay, so let's go back to our problem, and to refresh ideas, let us have the weak form which is given integral 0 to L EA U FE prime W prime plus K0 UFE W, okay, dx plus integral 0 to L K1 UFE cubed W dx this is equal to integral of FW dx plus PW at L. Okay. So, let us say that I have obtained the solution at the I minus 1th step. Okay. So, I minus 1th step solution. Okay. So, this will be given as UFE at the step I minus 1, which will be equal to sigma j is equal to 1 to number of nodes, okay, aj due to I minus 1 phi j, where phi j is my basis function globally. Okay. So, given the solution, now I can compute the residual. So, what will the residual be? So, I come back here, I say that now here by putting W is equal to phi k and so on, we get the form k which depends on UFE at the step I minus 1 into A at the step I is equal to Fi. This is what we had done earlier in order to solve for the AI. Okay. So, now what we will do is I will call K UFE at the step I, as we have done already, in order to discuss the residual, okay, minus this plus Fi is equal to the vector Ri. Okay. What does it mean? That because my solution, the current solution, is not the exact one, then this matrix system will not be equal to the load vector. If it was, then Ri would be 0. If it is not, Ri will be non-zero. Okay. So, this way I can compute Ri at each step. Okay. So, similarly, I will have minus of k UFE at the step I minus 1 into A at the step I minus 1, okay, plus F at the step I minus 1, this is equal to R I minus 1. Okay. So, this is what we have. Okay. So, I have the generic definition of the residual vector in terms of the generic solution vector A. Okay. So, then we say that I want to find, so given AI, given the vector A at the step I minus 1, find delta A, okay, such that the new residue is minimized. Okay. This is what we want. So we'll say that the residue, so given the solution at the step are at the step I minus 1, I want to go to the step I using this change in the ai minus 1 in such a way that the new residue is minimized. So what we will do is we will take the residue at the step I and expand it in a Taylor series expansion in terms of the delta ai minus 1 about the residue in the step I minus 1. So I want to expand, since the residue becomes a function of ai, I want to expand the ai in terms of ai minus 1, around a minus 1. This expression of in terms of ai, we want to expand it in a Taylor series expansion about ai minus 1. So this will become the residue at the step I minus 1, okay, plus we will have, I will write what this means, the partial of the residue, I will not write this as this, the partial of the residue with respect to the vector A evaluated at the step I minus 1, okay, into delta A into the vector delta A I minus 1, plus I will have higher order terms. Okay. So you see, when I take the partial of a vector with respect to a vector, I will actually get a matrix or a second order tensor. So we will come to that. Okay. Now we said that in the Newton-Raphson method it should be minimized, rather we say it should be 0. Okay. And we are ignoring the higher order terms in what we do. So we say that, well, I take the linear expansion about the solution obtained in the previous step, okay, and I will use that in order to obtain the new correction to the solution. So this will give me, this implies that del R del A evaluated at the step I minus 1 into delta A at the step I minus 1 is equal to minus R at the step I minus 1. Okay. So this is what drives our solution. So if you see this, this is a matrix which is now known given the solution at the step I minus 1. So this known matrix into this change or the perturbation in the coefficients part is equal to the minus R, and so from here we can find this. Now how do we write this del R? See, del R del A, okay. So this will be equivalent to saying that I want to find some matrix which I will call by, you will see the reason, KTIJ, the entry of it is equal to del Ri del Aj, okay, evaluated, because let me now change my naming system so that we don't have a problem here. Okay, I will say Lk. So del RL del AK evaluated at I minus 1. Okay. So how will I do it? What is RL? The nth component of the residue vector. So this will be from what we had done earlier in the definition of the residue. If you remember, in the first place we had, okay, this is the definition of the residue. Okay, so now let us go to what we want to do, and we will have this as FL minus K LK or LM, I will say, not K, LM, just to be generic, LM into AM. Okay. Now, so if I say implies del RL del AK is equal to del FL del AK minus K itself, KLM is itself a function of AK. Okay, so del KLM by del AK into AM minus again here we will have KLM del AM del AK. Okay, so in what we have taken, our F is independent of the displacement. In the case that I have a follower load where the load is changing with the configuration, F will also be a function of the displacement. Nevertheless, here it is 0. Okay, this quantity, if I look at it, it is equal to delta mk. That is, it is equal to 1 only when m is equal to k. So this delta mk, so this whole quantity will become k l k. Okay. So this is 0, this is gone. Then this quantity, from the expression that we have, KLM is equal to integral 0 to L EA phi L prime phi m prime plus K naught phi L phi m plus K1 U squared into phi L phi m. Okay. So this is my definition of KLM. Now UFE squared is in terms of these coefficients themselves. So this will become, then I will get delta KLM by delta AK. From the first part, if I come here, the first part, the derivative will give me 0 because this part does not have the AK sitting there. Okay, so this part will get knocked off. Okay, so this part will get knocked off. So the linear part will not contribute to this. Second part, I will find the derivative of it with respect to. So it will become integral from 0 to L from what we have done here, K1 twice UFE into derivative of UFE with respect to AK. What is derivative of UFE with respect to AK? It will be phi k. Okay, so it will be twice K1 UFE into phi k into phi L phi m dx. Okay. So now what do we have to do? So here you see that delta RL delta AK is equal to minus KLK plus or minus this part. So we will do that. So this quantity will now become delta RL delta AK is equal to minus KLK. This KLK contains both the linear and the nonlinear part. Okay, minus, I will get here integral 0 to L 2 K1 UFE phi K phi L phi M dx into, if I go back, this will be into AM. Okay, this will be into AM. So essentially, since M is occurring here twice, I get AM into phi M is nothing but a summation over this combined would be sum of A M phi M. Okay, and this would be equal to nothing but UFE. Okay, so this will be equal to minus KLK minus 2 integral 0 to L K1 UFE squared into phi L phi K dx, and this is my delta RL delta AK. Now you see here that this will have by itself minus of KLK linear minus KLK nonlinear. Now KLK nonlinear part, from what we have marked in the previous slide, will be equal to integral K1 UFE squared phi L phi K. So you see, from our definition what we have here, this is nothing but KLK nonlinear. Okay, so this will become equal to minus of KLK linear plus 3 KLK nonlinear. So this is what we are going to get out of this computation. So you have to be very careful here to see this part, that this part together they form UFE. Okay, so once I have this, then now I have the representation. This matrix, because it came from the partial of the residue with respect to the solution vector at the current solution vector, it is called the tangent stiffness matrix. So we have tangent stiffness matrix that is the local slope in the drawing that we have made in the beginning. Stiffness matrix is KT such that I will write what we mean by this. KTLK is equal to, for this problem, KLK plus 3 linear plus 3 KLK nonlinear. Okay, or this is also in the generic way del RL del A K at the step evaluated at the step I minus 1. Okay, so the components of the tangent stiffness matrix are obtained by taking the partial of the RL evaluated at this. So in this case, what will the tangent stiffness matrix entry be? Because we have to evaluate it, we have not done the evaluation at the previous step, so it will be for us in this problem KLK tangent, and I have thrown out the minus part. Why? Because this minus on this side, and if I go back, the minus here and the minus here will cancel them out, so we will be left with essentially the KT acting on delta A is equal to Ri minus 1. Okay, so we will have, let's say, KTLK will be equal to integral 0 to L EA phi L prime phi K prime plus K0 phi L phi K dx. This part remains fixed. You don't have to update this all the time. Once you have created this part, which is your K linear LK plus integral 0 to L 3 times K1 UFE at the step I minus 1 whole squared into phi L phi K dx. Okay, so this is nothing but KLK nonlinear. Okay, so for this problem, this is what we will get as a tangent stiffness matrix at the step I minus 1. So let me go back to my drawing here. So it is the local tangent or the local slope for the at the current solution level that we are talking about. Okay, so this way we can construct the tangent stiffness information each time, and so I will get the KT, okay, into delta A at the step I minus 1. This is equal to R at the step I minus 1. Okay, what is R at the step I minus 1? It is by putting UFE at the step I minus 1 in the expression for the stiffness matrix and the load. Okay, so this will be K due to UFE at the step I minus 1 into A I minus 1 minus of this plus F at the step I minus 1. Okay, so this is how we are going to get the residue vector, and once we solve this, then we are ready to, we can compute this by inverting KT. You see the feature of KT will also be symmetric for this problem. Okay, so it will be symmetric, it will be invertible. What do you do with respect to the boundary conditions on delta A? So if I have this bar, remember, with F here, okay, so here my U is given as 0, let's say, so, or it could be given as some other value, but wherever the U is specified, my delta A has to be 0 at that point. Okay, so I would get my delta A1 for any step is equal to 0 if I take a, let's say, a 3-element mesh. Okay, so I could have the U given as U0 bar, U0, which is non-zero. In that case, I will get some contribution due to this basis function. Okay, but my delta A1 here has to be 0. Okay, this condition has to be enforced. We enforce it using the standard penalty formulation, or the way we have been doing it, and we go ahead and solve for delta AI. We get the solution, use it, update. AI will be equal to the vector A I minus 1 plus delta A I minus 1. Okay, this way we go ahead and construct the solution in an iterative way, and we stop using the stopping criteria that we had mentioned earlier. Okay, so now the question is, how do we do it at the element level? Again, we have let's say a mesh of some elements. Let me pick a generic element in. Okay, in this element, let's say I have these basis functions which are non-zero. Okay, I'm taking a linear approximation to bring the point out. So it will be corresponding to the node n and n plus 1, phi n plus 1. Okay, so this is what we will have at the element level. So what we are going to do is, at the element level, we are going to compute the k linear for the element n, k nonlinear for the element n. How do we compute? So it will be essentially, if I have a piecewise linear approximation, this will be a 2 by 2 matrix, this will be a 2 by 2 matrix. Okay, this one we can compute once and for all and keep it, or we can redo every time depending on the size of the problem and the convenience we have with respect to storage. Okay, so then this k ij linear in the element n will be equal to integral x1 of the element n to x2 of the element n ea ni of the element n prime nj of the element n prime plus k0 ni of the element n nj of the element n. This is where I and j goes from 1 to 2. In this case, in the generic case, it will go from 1 to p plus 1. Okay. Similarly, kij nonlinear in the element n will be equal to integral x1 of the element n to x2 of the element n. Okay, k1 into ufe from the step I minus 1 in the element n whole thing squared into ni in the element n, nj in the element n dx. Okay, what is this ufe in the element n? This will be sigma I is equal to 1 to p plus 1. Okay, a for the element n I, or I would put it as L, a L of the element for the step I minus 1, okay, into n L for the element. This is what my UFE in the element will be. Now what is a n I minus 1? This will come from the global to local enumeration. So we have to keep in store the solution at the previous step, that is at the I minus 1 step, from where we extract the coefficients, use it to construct the solution at the function UFE in the element. Now we go to numerical integration. We will evaluate this function at each integration point, find the square of it, put it there, multiply with the value of the shape functions ni and j at these integration points, and we do the summation as usual. So this will give me the element wise the nonlinear stiffness matrix. Okay, then we follow the usual assembly procedure using the global local enumeration that we had talked about till now. Okay, so here we have outlined a procedure with which we can construct solutions to nonlinear problems. So we could also do the same for the case of large deformation problems where the strain Exx is given as del u del x plus, let's say, half of del u del x whole squared. Okay, let's say we use the standard strain energy expression, then minimization of the total potential energy. Here this can be put in the expression for the total potential energy pi, okay, which will be in terms of u minus v for the bar problem. Okay, this u will have half integral 0 to L EA EXX whole squared dx. Okay, so we'll have exactly the same scenario as we got in the previous problem, where this quantity is now going to contribute to the nonlinearity, this quantity. Okay, so when we take the first variation of pi, from there we'll get a nonlinear expression in terms of del u del x. Again we do the same procedure of finding. If I am using the direct solution, then I will go ahead and find a solution using this solution. I am going to update my solution to the next solution. Or if I am using the Newton-Raphson method, I'll have to find the tangent stiffness matrix arising out of this expression. Okay. Similarly, I can have the case of the nonlinear beam deformation, where in the case of the beam, Exx would be equal to del u naught del x, okay, minus z del w del x plus half del w del x whole squared. This is the von Karman theory from the von Karman theory. Again you see that in the strain itself I have this nonlinear term in terms of del w del x sitting, okay, and del 2 w del x squared here, okay, sitting there, and this again has to be taken care of in following the same procedure that we had followed till now. Okay. Now the other issue is that when I have a nonlinear time dependent problem, so in this case it is a good idea that, let's say I want to go to a particular load level. Okay, so let's say this is my f. So it's better, in fact I could have done it for the problem that we had been discussing till now in the Newton-Raphson regime, that I break the loads into the small steps, delta f1, delta f2, delta f3, and so on. Okay, and I solve the problem in steps for these incremental loads. Now when I am in a time dependent regime, then I'll have to frame first the semi-discrete formulation with the nonlinear stiffness matrices sitting there, okay, and the mass matrix, if it is nonlinear, sitting there. Okay, then at every time station, so I am at a time station, so delta t, so I am at a time station I minus 1. I want to go to the time station I, okay, using the delta t. Okay, then here I set up the nonlinear system of equations. Okay, and we can use the standard Newton-Raphson strategy that we have done, okay, and we can solve this. So the good idea will be that break this into small steps. The time station is broken into small steps. For that time station, the load is broken into small steps. That is the amount by which the load increments. Okay, so this is my t, this is my f. Okay, so I will have this. Okay, so I will go to these increments in the load, and then I will solve the problem accordingly. Okay, so I'll have to set up the nonlinear system of equations at every time step and go ahead and solve it. Okay, this procedure has to be handled in a very careful way, especially the convergence or the stopping criteria has to be properly formulated, boundary conditions have to be properly imposed in order to get a good solution. Okay. If there is something wrong in the code, you will see that the number of iterations taken for convergence will increase significantly, or you may not even converge. Okay. Next is, if you look at these problems where it does happen that the load response curve does something like this, then we have to get into something called, here we are increasing the load really. So this is called the generic approach is called the load control approach. Now if I have this kind of a situation, I'll have to go to a displacement control approach. Okay, which means that at this point I cannot really go beyond this point with my load control approach, because here the tangent stiffness matrix will become singular. Okay, so I have to do something in order to come to this part of the solution, okay, where I go to this displacement control, or we'll use the so-called continuation methods which are available in the literature. There is a nice code which is downloadable from the Pittsburgh site called PitCon, which is Pittsburgh continuation method code, okay, which will solve all these exotic problems where the solution does this kind of a behavior or it does this. This is called a snap through, this is called a snap back. Especially this kind of a situation, the snap through situation, arises when I have an arched member and I am applying a middle load. So what will happen, this member will initially deform like this, okay, slowly as the load is increased, and suddenly it will come to this configuration, okay, where it will become stable. After that it will keep on deforming like this. So it snaps to this configuration and then it becomes sufficiently stiff. Okay, so all these things can be done, but for that you need to go to these advanced courses. So the bottom line in this course has been to enforce the concept of the series representation of the approximate solution in terms of the special basis functions which we have created, okay, which this creation of the basis functions is essentially the heart of the finite element method, okay, because they have local support, they have the continuity requirement that we have enforced, okay, and it is possible using this approach to tackle any problem, come up with the variational formulation or the weak form, and construct suitable approximations to the problem. Okay, with that we would like to stop here.